Okay, let's unpack this. We are living through what I can really only describe as the instruction following boom.
Oh, absolutely.
It's the era where you type something into a chat box, whether that's GPT-4 or Claude or whatever flavor you prefer, and you give it a command, and it just does it. It feels entirely like magic.
It does. But behind that magic is a massive, expensive, and frankly, a very exclusionary wall.
Right.
It creates a serious bottleneck, doesn't it? I mean, you look at these incredible models and think, wow, I want to build one of those.
Sure. Yeah.
But then you look at the price tag. The development costs are astronomical. The compute requirements are massive. We are talking data centers the size of football fields here.
Yeah.
And the best ones are locked behind closed doors.
Yeah.
It creates a situation where only the absolute biggest players can really play the game.
Exactly. It's the rich get richer problem of AI. And I
Yeah.
think that's why when Stanford released Alpaca a while back, people just went absolutely nuts.
Oh, they did. It was a huge moment.
It was this moment of, hey, wait a minute. We can take an open source model like Llama, fine-tune it to follow instructions, and actually have something usable on our own hardware.
Right.
And there was always but in tech, right. Even Alpaca had its baggage.
It did. Definitely, the Alpaca was a breakthrough, certainly. It proved that open source models could be fine-tuned to follow instructions almost as well as the proprietary giants.
Mm-hmm.
But to do it, you still had to update all 7 billion parameters of the LLaMA model.
Which is heavy.
Extremely heavy. It is slow, it is computationally expensive, and it's hard to iterate on. You're essentially retraining the whole brain just to teach it some basic manners.
Wow.
You're rewriting the entire neural network just to teach it specific behavior.
So that brings us to the star of today's deep dive. We are looking at a paper titled LLaMA-Adapter, Efficient Fine-Tuning of Large Language Models with Zero-Initialized Attention
He is a bit of a mouthful.
by Zhang and colleagues, yeah. And if that title sounds like a wall of jargon, stick with us because the numbers in this paper are absolutely wild.
They really are. The headline here isn't just about performance. It's really about efficiency.
Right. So what is the mission here?
The paper proposes a method to turn a frozen static LLaMA model into an instruction-following powerhouse. But here's the key statistic. Instead of updating 7 billion parameters, they introduce only 1.2 million learnable parameters.
Wait, let me just pause on that for a second. 7 billion versus 1.2 million.
Yeah.
That's not even close. That is basically a rounding error.
There's a reduction of magnitude that is just hard to overstate. It's a fraction of a percent of the total model size.
And what about the speed? Because usually when you shrink things down that much, you trade off speed or you trade off quality.
Not here.
Yeah.
They actually managed to fine-tune it in less than 1 hour using 8 A100 GPUs.
Less than an hour.
Yes. That is about 3 times faster than Alpaca.
Okay. And the storage. This was the part that just completely blew my mind when I was reading the source material. The full Alpaca model, the one everyone was so excited about, is something like 13 gigabytes.
Right. It's massive.
You can't just email that to a colleague.
No.
But the adapter,
Yeah.
the thing that actually makes it smart, it is roughly 4.7 megabytes.
4.7 megabytes. Yes.
I have photos on my phone larger than that.
Huh?
I have MP3s of mediocre 90s pop songs larger than that.
Yeah. It is incredibly efficient. It's the difference between needing a moving truck to transport a library versus just carrying a single index card in your pocket.
It completely changes the logistics of how we can distribute AI models, doesn't it?
It changes everything about the logistics, yes.
So the mission for this deep dive is to figure out exactly how they pulled this off without making the model stupid.
Right.
We are going to look at this zero-initialized attention mechanism, which seems to be the secret sauce here, and we're going to talk about something really cool later on. This thing can actually see. It is not just text. It handles images, too.
That is right. It is a multimodal breakthrough just as much as it is an efficiency one.
Okay, let's start with the basics then. Section 1, let's call it the frozen brain. You mentioned earlier that with LLaMA-Adapter, we aren't retraining the whole brain. How exactly does that work?
So imagine the pre-trained LLaMA model, the 7 billion parameter version, as a highly educated encyclopedic brain.
Okay.
It knows how to structure sentences, it knows facts about the world, it knows history and math. In the traditional approach, like what Alpaca did, you go in, you slightly tweak every single neuron in that brain to teach it a new task.
Which risks messing up what it already knows, right?
Precisely. It is highly invasive. It's like doing brain surgery to teach someone how to play the piano. You might teach them the piano, but you might accidentally make them forget how to speak French.
Oh, wow.
This is a known issue. It is called catastrophic forgetting.
Right, and obviously we want to avoid that if you are building a useful tool.
Exactly. So LLaMA-Adapter takes a frozen approach. It keeps that original 7 billion parameter model completely static. It does not touch the original weights at all.
So the brain stays exactly as it was, it's locked down.
Correct. Instead, they insert what they call learnable adaptation prompts into the transformer layers.
Adaptation prompts, is that sort of like giving it a cheat sheet?
In a way, yes. Think of them as additional context clues that act as prefixes to the actual input. But here is a very specific detail from the paper that matters. They don't just sprinkle these prompts everywhere.
Oh, where do they put them?
They insert them specifically into the topmost layers. They denote it as L layers in the math, and the paper specifies they use the last 30 out of the 32 layers.
Now, why the top layers? Why not the bottom ones where the raw data comes in? If I want to change how the model thinks, shouldn't I be influencing it from the bottom up?
You would naturally think so, but in deep neural networks, the layers function hierarchically.
Okay.
The bottom layers are processing basic features, syntax, grammar, very fundamental plumbing kind of stuff.
Right.
The top layers are where the higher level semantics live. That is where concepts, reasoning, and complex understanding happen.
Ah, so by targeting the top 30 layers, you are trying to steer the reasoning, not the grammar.
Exactly. You are tuning the model's high-level understanding without getting bogged down in the basic wiring.
Okay, so we have this frozen brain, and we're pasting these new prompt layers on top to guide it. But here is the problem the paper highlights, and it makes intuitive sense to me.
Go ahead.
If I just shove a bunch of random prompts into a genius brain, isn't that just going to be noise?
It is exactly noise. And that is the fundamental problem with using adapters traditionally.
Right.
If you initialize these prompts randomly, which, by the way, is standard practice in machine learning,
Yeah.
you are effectively shouting gibberish at the model at the very beginning of training.
So the model is trying to process your input, but these new adapters are just screaming static at it.
Right. It disturbs the original knowledge. The model gets confused because these new inputs don't mean anything yet, but the architecture is treating them as valid data.
That sounds chaotic.
It is. So the loss curve, which is the metric that measures how wrong the model is, starts really high. And the model spends the first big chunk of its training time just trying to figure out what to ignore.
So you're trying to teach it to follow instructions,
Yeah.
but you start by essentially blinding it with static. That sounds wildly inefficient.
It is very inefficient. And that brings us perfectly to the core innovation of this paper. Section 2, zero-initialized attention.
This is the secret sauce we talked about.
This is the elegance of the math in this paper. To solve that noise problem, the researchers introduced a learnable gating factor.
Okay.
They denote it in the math as GL. And the most crucial detail is right in the name. This gate is initialized at 0.
Okay, let's use an analogy for everyone listening, because the math can get dense. I'm thinking of a dimmer switch.
That is a perfect analogy.
So imagine a dimmer switch controlling a spotlight. The spotlight represents the influence of these new learnable adaptation prompts.
Right.
When you start training at minute 0, the dimmer switch is turned all the way down. It is set to 0.
Exactly. Because the gating factor is 0, the adaptation prompts contribute absolutely nothing to the attention scores. The model behaves exactly like the original frozen LLaMA model. It ignores the new guys completely.
So there is no confusion, no cold start noise at all. The model is stable from the very first second.
Zero noise. But as training progresses, that gating factor, your dimmer switch, starts to become learnable itself.
It slowly turns up.
Yes. The value changes from 0, and it starts progressively injecting those new instructional cues into the model's reasoning process.
So it's a completely smooth transition. It goes from I am just regular llama to I am llama, and I'm quietly listening to these new instructions.
Exactly. It transforms the training process from a messy repair job into a smooth integration. And the math backs this up beautifully.
How so?
They use a tan activation function and separate softmax functions for the prompts and the words.
We don't need to do the calculus on air, but what does that actually achieve practically?
Basically, it ensures that the pre-trained knowledge, the word tokens,
Yeah.
preserves its original probability distribution.
Okay.
They aren't warping the library, they're just gently guiding the librarian.
But does it actually work better? Or is it just a really nice theory?
The results are pretty stark. The paper shows a direct comparison of the loss curves. With random initialization, the old way, the loss starts high and stays high for a while. It gets stuck.
Right, fighting the static.
Exactly. But with zero initialization, the loss drops dramatically right at the start and converges much, much faster.
So it learns faster simply because it doesn't have to unlearn the initial confusion.
Precisely. It creates a much more stable training process,
Mm-hmm.
and that stability is exactly what allows them to get such good results in less than 1 hour of training time.
Which is incredible speed.
Yeah.
But you know what I love about this paper is that they didn't just stop at text. They looked at this mechanism and said, hey, if we can inject text prompts cleanly, can we inject pictures?
Yes, this is section 3, beyond text. This is where LLaMA-Adapter shifts from being just a really efficient text bot to a true multimodal reasoner,
Image-conditioned instruction following.
which is just a very fancy way of saying I can look at this picture and answer your questions about it.
But how do they actually plug an image into a text brain? I mean, the llama doesn't have eyes.
No, it doesn't, but it has compatible slots now.
Okay.
They use a pre-trained visual encoder. Specifically, they use scalability, which is very standard in the industry right now. It looks at the image and extracts multi-scale features.
Basically breaking the image down into mathematical descriptions.
Exactly. It turns pixels into numbers the network can understand.
And then?
Then they pass those features through a projection network. And here's the really cool part. They add them directly to those exact same adaptation prompts we just talked about.
Wait, so visually the image just becomes another set of prompts floating in the top layers of the brain.
Exactly. It plugs visual information directly into those learnable slots. And because of the zero-initialized attention, the model slowly learns to incorporate that visual data without forgetting how to speak English.
That is wild. The examples in the paper are really fun here, too. They have these moments where you really see it working in practice.
The Mont-Saint-Michel example is a classic one from the paper.
Yeah, I loved that one. They show the model a picture of that famous island commune in France, and the user asks, what place is this?
And LLaMA-Adapter correctly identifies it as Mont-Saint-Michel, Normandy, France.
But if you think about it, that requires visual recognition and accessing the text knowledge base about geography.
It does.
It has to see the spire, recognize the distinct island shape visually, and then go into its text memory and pull up the word Normandy.
Right. It connects the visual concept to the semantic knowledge perfectly. But my favorite example from the source material is the counting test.
Oh, the yellow blocks.
Yes. This really shows the precision of this method.
Hmm.
They showed the model an image with some colored blocks scattered on a table.
Simple enough task.
You'd think so. The prompt was simply how many yellow blocks are in this image.
Right.
LLaMA-Adapter correctly counted 2 yellow blocks, but they compared it against other multimodal models out there.
And how did the big dogs do?
Well, Mini GPT-4 guessed 6, and LLaVA guessed 4.
Wait, really? The other models were just hallucinating blocks that weren't there.
Yes. Multimodal hallucinations are a really big problem in the field. The models see blocks and they just start guessing numbers based on language probability, not on actual visual grounding.
They aren't counting, they're just predicting the next word.
Exactly. But LLaMA-Adapter was the only one in that direct comparison to get the count exactly right.
That strongly suggests the connection between the visual input and the reasoning center is much, much cleaner here.
It suggests that the zero-initialized attention allows for a very precise integration of those visual cues. It prevents the visual data from overwhelming the logic centers. It's not just running on vibes, it is doing actual counting.
They also had it reading text in images, right?
Yeah.
OCR.
Yes, optical character recognition. It looked at a picture of the Hollywood sign and correctly read Hollywood. And it even did navigation reasoning.
Oh, right. It looked at a sign on a wall. You know those confusing hotel signs?
The ones where arrows point everywhere, you end up at the ice machine instead of your actual room.
Exactly those. The sign said rooms 501 to 506 were to the right and 501 was to the left. Actually, wait, let me check the source on that.
Yeah, look at figure 6 in the paper.
Ah, right. The user asks, where should I go if I want to go to 501, left or right? And the sign has an arrow pointing left specifically for 501, and LLaMA-Adapter says left.
And the competitors.
Let's see. LLaVA gets completely confused by the other numbers on the sign and gives a really long explanation but misses the point. Mini GPT-4 just says right, which is flat out wrong.
So it is highly functional, it's practical. Which brings us to the showdown.
Section 4.
We have talked about the tech, but how does it actually stack up against the competition in the formal benchmarks?
Right, because anecdotes are great, but the benchmarks tell the real story.
Well, the primary comparison in the paper is against Alpaca, the full fine-tune.
Heavyweight.
The heavyweight, yes. And the qualitative results The actual text generations is totally comparable. They show examples of it writing code for Fibonacci numbers, translating, "I have no mouth, but I must scream" into Spanish.
A cheerful prompt?
Very. But the quality is indistinguishable from the fully fine-tuned alpaca model.
But with a fraction of the parameters.
A tiny fraction. But the even more interesting comparison is against alpaca LLaMA.
Now, LoRa is the other big efficiency method everyone is using right now, right? Low-rank adaptation.
Correct. LoRa is basically the industry standard for efficient fine-tuning. But look at the stats here. Alpaca LoRa uses about 4.2 million parameters. LLaMA-Adapter uses 1.2 million.
Wow.
So it is nearly 4 times smaller than its most efficient competitor.
That's a huge difference in sheer efficiency. But does it actually beat it in a blind test?
They ran the GPT-4 evaluation benchmark.
Which is where you have GPT-4 act as the judge between two different models, right?
Exactly. You ask GPT-4 which answer is better. And LLaMA-Adapter scored more overall wins against Alpaca and Alpaca LoRa in direct head-to-head comparison.
That is seriously impressive. It's leaner and meaner.
And then there's the Science QA benchmark. This is a massive data set of science questions, some with images, some without. LLaMA-Adapter multimodal achieved 85.19% accuracy.
Is that good for that benchmark?
It's excellent. For context, that beat GPT-4 using chain of thought, and it beat ChatGPT on this specific data set.
Wow.
But here is the real kicker regarding our dimmer switch analogy from earlier. Adding the zero-initialized attention boosted the accuracy by over 43% compared to random initialization.
43%? Wait, that is not a marginal gain.
No, it is massive. Random initialization got stuck at around 40% accuracy.
Which is basically just guessing.
Exactly. Zero init shot it all the way up to 85%. That proves the mechanism isn't just a clever tweak. It is literally the difference between the model working and failing.
It completely validates the hypothesis that early noise was killing the performance of the other models.
That is a massive validation of their entire method, yes.
So if you're listening, just think about this. We have a model that is tiny, it's fast to train, it works flawlessly with images, and it beats the standard benchmarks. What does this mean for the future?
This brings us to Section 5. Let's call it the plug with expertise future.
I like that.
This is where I really get excited about the real-world application. Because the adapter is so small, remember, we are talking 4.7 megabytes.
All right.
You don't need to copy the whole 13-gigabyte model for every single new task you want to teach it.
Right. Usually if I want a medical bot, I have to copy the whole giant brain. If I want a coding bot, I copy the whole brain again.
Exactly. And very quickly, you run out of hard drive space. With this method, you have one base LLaMA model sitting frozen on your drive.
Just the one big file.
Just one.
Yeah.
Then you can have a folder of tiny little files. One file for coding, one file for French translation, one file for visual reasoning.
And you just hot swap them.
You swap them in milliseconds depending on what you need. It entirely separates the general intelligence from the domain expertise.
And does this work for other models? Or is this just a neat trick for LLaMA?
The paper explicitly shows generalizability. They tested this method on VAT, that is a vision transformer, and it worked. They tested it on Roberta, a popular language model, and it worked. They tested it on CLP for vision language tasks.
And did it hold up?
It consistently outperformed other parameter-efficient methods like SideTune and VPT on benchmarks like VTABI1K.
So this zero-initialized attention concept is a fundamental discovery in AI architecture, not just a hack for one specific model.
It's a fundamental breakthrough. It really opens the door for running these incredibly smart models on edge devices.
Edge devices, meaning local hardware.
Exactly. If you can store the expertise in a 4-megabyte file, you can put expert-level AI on a phone, on a drone, maybe even a smart appliance, without needing a constant connection to a massive data center.
It really democratizes the tech.
Yeah.
If you're listening to this, it means you don't need a server farm to build a custom AI anymore. You just need 1 hour on a decent GPU setup and a file small enough to text.
Exactly. It completely lowers the floor for innovation. Anyone can play the game now.
Okay, let's bring it home. Recap time.
LLaMA-Adapter. It is lightweight, just 1.2 million parameters. It is incredibly fast, less than 1 hour to train. It is stable, thanks to the zero-initialized attention dimmer switch.
Yep.
And it successfully turns a frozen large language model into a highly capable instruction-following image-reading expert.
And it does all that while being small enough to email to a friend as an attachment? That is the part I honestly still can't get over.
It really challenges the whole assumption that bigger is always better in AI. Sometimes smarter integration is better.
Smarter, not harder. So here's my final provocative thought for everyone listening to this deep dive. We have talked today about injecting cited instruction following into this massive digital brain using a mechanism as small as an MP3 file.
Right.
If we can plug in cite and we can plug in coding skills so easily, what else can we plug in next?
That is the question.
Are we moving toward a future where we carry a literal library of thousands of expert adapters right in our pockets? Imagine walking into a mechanic shop, downloading the car repair adapter directly to your smart glasses, and suddenly you are a master mechanic. Or downloading a surgery adapter in a medical emergency.
It is very much the Matrix concept, isn't it? I know Kung Fu,
Yes.
but instead of downloading it into your own biological brain, you download it into your AI assistant in a split second.
Exactly. The ability to just hot swap skills into a general intelligence on the fly might be the next truly big shift in how we interact with AI.
And with files this small, the friction to actually doing that in everyday life is practically zero.
It is definitely something to chew on. Thanks for diving deep with us today on LLaMA-Adapter.
Always a pleasure to be here.
We will catch you on the next deep dive.